In this lesson, I'm going to go over models for population growth, specifically logistic growth, logistic differential equations, and carrying capacity. Our first definition is logistic growth. We have a rate of change of y may be proportional both to the amount or size of the quantity and to the difference between a carrying capacity m and its amount size. Next, we have a general logistic differential equation. The formula is dp dt equals kp times the quantity m minus p. So anything of this form is going to be a logistic differential equation. If you take a logistic differential equation and you solve it using your initial condition, what you'll get is a solution which will be in this form. It's p equals m carrying capacity divided by 1 plus ce to the negative mkt. And then if you take this equation and graph it, you'll get a curve that looks like this. So there's a couple of things going on. Our x-axis is t, and then our y-axis is p of t. You have right here the value m. M is the carrying capacity. And then half of m right here, m divided by 2, that's where the point of inflection occurs. And I have it written out here, the greatest rate of change occurs when the population is half of the carrying capacity. So the greatest rate of change, or the point of inflection, occurs right here at m divided by 2. And then regardless of the initial condition, as t gets larger and larger, the limit of the curve is going to equal m. So as t gets larger and larger, the curve will approach the height m, or carrying capacity. This example says, given the differential equation, dp dt equals 0.8 p minus 0.004 p squared, identify the carrying capacity. So the first thing we want to do is we want to get this equation into this form right here. dp dt equals kp times the quantity m minus p. When the differential equation is of this form, where kp is factored in front, and then you have parentheses m minus p, this number right here is going to tell us the carrying capacity. So we want to figure out what to factor out so that inside the parentheses we just have left a number minus p. So looking right here, if we factor out 0.004p, you'll just be left with minus p. So one more time, when we factor 0.004p out of this term, it leaves just minus p, and that's the form we need for our differential equation. So when we have 0.8p and we factor out 0.004p, we just need to figure out what's left here. So I'm just going to go 0.8 divided by 0.004, and it's 200. So now that we have dp dt in this form, this is kp times the quantity m minus p. So m is the carrying capacity. So our carrying capacity is 200. This example says the population p of t of a species satisfies the logistic differential equation dp dt equals p times the quantity 2 minus p over 5,000, where the initial population p of 0 equals 3,000, and t is the time in years. What is the limit as t goes to infinity of p of t? So again, when you have a logistic differential equation of this form, its solution looks like this, and then when we graph this curve, you get this graph right here. And it says regardless of the initial condition, the limit as t goes to infinity of p of t equals m, and m is the carrying capacity. So in order to answer this, we just need to know the carrying capacity. And to do so, we just want to get this in the form of kp times the quantity m minus p, and then we can identify the m, which is going to be right here. And right now, this p is being divided by 5,000. So we want to factor out 1 over 5,000. We want to bring that to the front. So I pulled 1 over 5,000 to the front. We still have p right here. And then that would leave this as minus p. So we just need to figure out what goes here. When we factor out 1 over 5,000 from 2, it leaves 10,000. All right, so at this point, you can see that the carrying capacity is 10,000. And then finally, it says, what is the limit as t goes to infinity of p of t? And this limit equals m. M is 10,000, so this limit equals 10,000. So our answer is D. This example says the growth rate of a population P of bears in a newly established wildlife preserve is modeled by the differential equation dp dt equals 0.008p times the quantity 100 minus p, where t is measured in years. Part A says what is the carrying capacity for bears in this wildlife preserve? Since this logistic differential equation is of the right form, kp times the quantity m minus p, you can see the carrying capacity is right here. So the carrying capacity is 100 bears. Part B says, what is the bear population when the population is growing the fastest? And again, from the graph, the greatest rate of change occurs when the population is half of the carrying capacity. So it's growing the fastest right here at m divided by 2. So I wrote that out. The population is growing the fastest when m is divided by 2, and that's going to be 50 bears. Part C, what is the rate of change of population when it is growing the fastest? The rate of change of population is described by dp/dt, and it's growing the fastest when population is 50 bears. So we're going to plug in 50 for P. So we take 50 and we plug it in here and here for P. So we get 0.008 times 50 times the quantity 100 minus 50. And I'm going to go ahead and plug this in the calculator. So you end up getting 20 bears per year. This example says the rate of change dp/dt of the number of people at a concert is modeled by a logistic differential equation. The maximum number of people allowed in the concert venue is 1,200. At 9 p.m., the number of people at the concert is 200 and is increasing at the rate of 400 people per hour. Which of the following differential equations describes the situation? So I want to identify a couple of things. The maximum number of people allowed in the concert venue is 1,200, so that's our carrying capacity. At 9 p.m., the number of people at the concert is 200, so that's our initial population. And it says that the population is increasing at a rate of 400 people per hour. So that's going to be our dp/dt. So again, we're going to use our logistic differential equation, dp/dt equals kp times the quantity m minus p. So we're going to plug these values in right here, and then we'll solve for k. All right, so everything's plugged in, and next we're going to isolate k. So we end up getting that k is equal to 1 over 500. So finally, when we plug in k and m into our logistic differential equation, we get dp/dt equals 1 over 500 times p times the quantity 1200 minus p. So our final answer is C. This example says, in a school of 3,500 students, the rate at which a rumor spreads is both proportional to the number of people who have heard the rumor and the number of people who have not heard the rumor. Suppose 20 students hear the rumor initially and that 200 have heard it after 2 hours. How many students will have heard the rumor after 5 hours? Sketch a graph of the logistic curve and state the window setting you used. Since the school has a population of 3,500 students, that's going to be our carrying capacity. So the equation we're going to use is the solution to the logistic equation. And again, we have m, or carrying capacity, is 3,500. It says 20 students have heard the rumor initially. So first we're going to use p of 0 equals 20 and that m is equal to 3,500. When we plug these into the equation, we can then solve for c. So we have 20 plugged in for p, 3,500 for m here and here. T is 0, and then we just have the 1 plus c. So let's go ahead and simplify this. So up here, this is just going to make 0, so e to the 0 is 1, and then all we have left is 1 plus c in the denominator. This is a proportion, so I'm going to bring this 1 plus c up to the left, and then I'm going to move this 20 down to the right. So now we have 1 plus c equals 3,500 divided by 20. This simplifies to 175, so c equals 174. Next it says that 200 people have heard the rumor after 2 hours. So we're going to plug in 2 for t, 200 for p, and then we also have this value for c, and then we still have the 3,500 for m. So we're going to plug all of that into this equation. So here's our equation with everything plugged in. First thing I want to do is multiply this negative 3,500 by 2. And we're going to do the same thing. This is a proportion. So this entire expression, we're going to move it up to the left, and we're going to bring this 200 down to the right. Next, we're trying to solve this equation for k. So we want to get k by itself. First thing we're going to do is we're going to simplify this fraction, and I'm going to subtract 1. And then we're going to combine this. So 35 over 2 minus 1 is the same as 35 over 2 minus 2 over 2. So that ends up being 33 over 2. Next, we want to get rid of this times by 174, so I'm going to multiply both sides of the equation by 1 over 174. And this fraction right here reduces to 11 over 116. And at the same time, I'm going to take the natural log of both sides. So at this point on the left, this is going to simplify to just negative 7,000k. And then last, we're going to get rid of this negative 7,000. All right, so here's our expression for k. And then next it says how many students will have heard the rumor after 5 hours. So we want to find p when t is 5 hours. So we have p of 5 equals, and then this is the equation where we have 3,500 for m, 1 plus, this is c, 174, e to the negative m, times k times t, where t is 5. So I drop down the 3,500, the 1 plus 174, e, and then right here, this is going to make 1/2. And I'm going to times it by 5. So really this is going to be 5 halves. And then I just drop down the natural log of 11 over 116. So next, we've been doing this in this chapter. I want to bring this 5/2 up to the exponent so it brings the e to the ln together, because when e is raised to the ln, those undo each other and it brings that expression down. So finally, we have 3,500 over 1 plus 174 times 11 over 116 to the 5/2, and I'm going to plug this into the calculator. So we end up getting, after 5 hours, 2,361.958 students have heard the rumor. And then finally, the problem says to sketch a graph of the logistic curve and state the window setting you used. So our logistic curve is P of t equals 3,500 over 1 plus 174 times the quantity 11 over 116 raised to the t over 2. So when you put this on the graphing calculator, you get a curve that looks like this. Your carrying capacity is 3,500, and then this is the window that I used. Someone else's window might look a little bit different, but you'll get this general curve. This example says a population is modeled by a function p that satisfies the logistic differential equation. So we have dp dt equals p over 5 times the quantity 1 minus p over 12. If p of 0 equals 3, what is the limit as t goes to infinity of p of t? So similar to the problems on the front, we want this to be in the form dp dt equals kp times the quantity m minus p. So first thing we want to do is we want to factor out this 1 over 12. So by factoring out 1 over 12 to the front, it's going to make 1 over 60p, and then 1 divided by 1 over 12 leaves 12 minus p. So now that the logistic differential equation is of this form, we can see that m, the carrying capacity, is 12. So we have carrying capacity as m equals 12. So we end up getting that the limit as t goes to infinity of p of t is going to equal that carrying capacity, 12. For part B, it says if p of 0 equals 20, what is the limit as t goes to infinity of p of t? And if you remember the definition on the front, it says regardless of the initial condition, the limit as t goes to infinity of the function will always be the carrying capacity, so it's still equal to 12. Part C says if p of 0 equals 3, for what value of p is the population growing the fastest? The population grows the fastest when m is divided by 2. So if m is 12, then 12 divided by 2 is 6. So when the population is 6, that's when it's growing the fastest. Part D says a different population is modeled by a function y that satisfies the separable differential equation dy dt equals y over 5 times the quantity 1 minus t over 12. Find y of t given this initial condition that y of 0 equals 3. So the first thing we're going to do is we're going to separate our variables. So we're going to move this y down to the left, and then we'll bring this dt up to the right. Next, I'm going to take this 1/5 and distribute it in, and we're also going to integrate both sides. So let's go ahead and integrate. And now we're going to take the initial condition y of 0 equals 3, and we're going to plug it in. So we'll plug in a 3 here for y, and then 0 for t. So we end up getting that c is equal to the natural log of 3. So now that we have c, we're going to plug it back in right here. And next, to solve for y, we're going to exponentiate both sides using base e. So at this point, these will undo each other, and we'll just have the absolute value of y. So over here, we'll split it up, e to this power times e to that power. And then this will just make 3, so we're going to take that 3 and multiply it to the front. And then I brought this y out of absolute value by bringing in a plus or minus on the right side. So we want to verify, do we use the plus or the minus? So I want to look back at the initial condition. For our initial condition, our y value is positive, so we're checking the positive option, and we're plugging in 0 for t and 3 for y. This is going to make 0, e to the 0 is 1, so we end up getting that 3 does equal 3. So it checks out, so we are going to use the positive option. So I wrote it out. Since y equals positive 3e to the 1/5 t minus t squared over 120 satisfies the initial condition y of 0 equals 3, this is going to be the equation for y of t. Part E says for the function y found in part D, what is the limit as t goes to infinity of y of t? So we're looking at this equation, and as t gets larger and larger, this function is going to go to 0. All right, guys, thanks so much for watching.